Here we're going to give an introduction to trigonometry, and the main reason for giving this video is just to sort of orient ourselves in trig. Why are we even studying trig? And it turns out there are two good reasons. The first reason is because it's going to allow us to study wave motion. So let me write that, wave motion. And you can also think of that as oscillatory behavior. Oscillations, just wiggling back and forth basically. Okay, and the second reason for studying trig is because it allows us to basically solve triangles. So let's write that we're going to be solving triangles. Try it again. Solving triangles. Okay, so I would say these are the two big reasons for studying trig. Let's go ahead and take a look at them. Let's go ahead and look at solving triangles first because that's a little bit easier to explain. So when you're solving triangles, what you're basically trying to do is you're trying to figure out the angles and the sides of a triangle. So for example, let's look at an application to astronomy. Let's say you were right here where this dot is, and you were looking out at the night sky and you saw a couple of stars. And let's say that you were able to determine the distance to the first star. So let's check that. You've got that. And let's say you were able to somehow come up with a distance to the second star. And let's say you were also able to ascertain the angle between those two lines of view. So you knew this angle as well. A question you might ask yourself is, given that information, that is this length, that length, and this angle, can you figure out what the distance is between those two stars? In other words, can you find that distance? And the answer is yes, you can do that using trig. So solving triangles is important because when you're able to find the angles and the lengths, for example, of sides of a triangle, you can apply it to fields like astronomy, which is sort of like the heart and soul of physics, or the beginning of physics, if you will. So that's one important reason for studying trig, and we're going to be doing a lot of that towards the end of the course. There's another reason as well, and it's what I first mentioned, which was to do with wave motion. Let's take a look at that now. So if you think about wave motion, if you recall from algebra what you have done and what you know so far, you've studied functions that were linear, and all I mean by linear is, just you've gotten these lines. And lines were useful when you were studying slope or grade of roads. This was an application of slope, the grade of some steep pass or something like that. And then you went on and looked at functions that were quadratic, and quadratic were simply parabolas. But you looked at quadratic functions in the context of maybe you were looking at the path of a ball under the influence of gravity. This might have been an application for quadratic functions, for parabolas when you were studying them. You further went on to study exponential functions, and this is an increasing exponential function, if you remember from algebra. And these came up in the context of population, like how a population might be growing. A population could be a population of humans or maybe of birds and so on, right? So this was a common application of exponential functions. Another one was finance. So your class may have studied exponential functions in the context of finance. And even though you may not have done this one, you still studied rational functions, or you were probably exposed to those. And an application of rational functions, you use these when you're studying changing gravity. That is how gravity changes as you sort of move away from the source. Or it comes up in what's called electricity magnetism. Let me just write electrostatics. So basically studying how the electric field changes as you get away from it. And the reason that's because those obey what's called an inverse square law. Inverse square law. And all it means is that you end up getting a function that looks like this, 1 over x squared. So this is an example of a rational function, and the graph would look something like this. Anyway, so for all the functions for a lot of the functions you talked about in algebra, you had these nice applications to them. But there's something that's sort of conspicuously missing from this list, right? If you think about the natural world we live in, what dynamic has not been sort of accounted for here. And the answer, of course, is wave motion. So when we talk about wave motion, what about wave-like behavior? We mean, just the obvious, water waves, right, in the ocean or in a lake. Or maybe sound waves as you're listening to this. Your ears are responding to a sound wave. Or even light waves, of course. You're able to see this? Okay, so algebra, in the land of algebra, we haven't really looked at wave-like or periodic behavior. And the question is how are we going to get functions that look like waves? And the answer is trig. That is one huge goal of trig, is to develop functions that allow us to describe wave-like behavior. Now the question is, how are we going to get that? What's a natural way of creating a wave? So over here we're going to end up with a wave, and the question is, how are we going to design that? Well, what we're going to do is we're going to look at a circle. So here I've got a circle, and imagine you had a point right here, and that point is, let's say, going to be at different locations around the circle, okay? And for different locations, I want you to notice two things. First of all, I can create this angle right here, which is going to be called our central angle. I'm denoting that with a little letter theta. So for wherever the point is, I'm always going to have some angle. And I also, for a given angle, have this length right here, okay? This is just some vertical length we're talking about. Now, what's going to happen as this point moves around? Well, let's say the point was over here. Let me draw it like so. Okay, if I draw in a little triangle like that, again, well, I've got a new angle, and let me ask you, is the angle smaller or bigger than the previous angle? Well, certainly bigger, right? Before the angle was just this, that little angle right there. Now the angle's, whoa, is pretty big. And the point's up here. Now, what about the length? Well, the length from the x-axis was that, was this. But then as the point moved, now the length is bigger. Okay, so two things have happened. The angle's gotten bigger, but the length of this line segment's gotten bigger as well. Now imagine that point keeps going along the circle. Okay, here, whoa, the length is really big. Okay, but as the point makes its way, like maybe over here, and you draw in the triangle again to the x-axis. So we're drawing always the triangle with the x-axis, like so. What's happened? Well, now the angle is really big, right? The angle's, boom. The angle is just continually growing, right? But what's happened is the length is getting smaller. So let's track what happens to the length. The point is moving. It's getting bigger, bigger, bigger. This length is getting bigger. And then all of a sudden it peaks, and the length starts getting smaller, right? All these lengths are smaller. So if we think about this angle, just this amount of rotation, constantly increasing, let's think about that amount of increasing along the x-axis, along this axis, okay? The angle's just getting bigger and bigger. Let's track what's happening to this length. Bigger, bigger. Peak, now it's getting smaller, okay? And as it goes below the x-axis, let's track the size, but make it negative because it's below the x-axis. So if the point is now, let's say over here, okay, again, I'm drawing a triangle to the x-axis. Here's my point now, okay? The angle's, whoa, really big, right? Large rotation. But this length is starting to grow again, but negatively, okay? So it's growing, and then once it's here, it's sort of grown all it can grow, or it's beyond, it's starting to shrink again, right? The length is getting smaller now as the point moves like this. So the length is getting larger, smaller, larger but negatively, still negative but smaller. And then what happens? And then it repeats that cycle. So if you track, as the angle increases this way, if you track that length, it's getting larger, 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 right? And then it peaks right here, larger, and then it starts getting smaller, and then it goes negative, and so on. Do you see that wave that's going to appear? So we're going to be able to get a wave if we think according to movement along that circle. Let's go ahead and draw that wave in now. So we're going to get this function that just rises and then falls, and then rises and then falls, and so on. And we're going to get this wave-like phenomenon, or wave-like function, that we can apply to all these different types of wave-like behavior. Now, when we do that, to begin this sort of discussion, we have to think about the angle, right, as we mentioned. And when we measure angles, when we apply all this to calculus next semester, we're going to be measuring these angles in what are called radians. okay, and radians, not degrees. So even though up to now you've measured angles in degrees, there's another way of measuring this angle called radians that's going to allow results in calculus to come out clean and in a useful way that degrees won't allow. Okay, so the first thing in our path to studying wavelike behavior is to think about angles in radians, and then once we've done that, then we can go ahead and create functions to describe wavelike behavior. Okay, so that's where we're headed with trig. Until next time.